In the middle of the Taklamakan Desert, where a single night of wind can bury an entire convoy, China has built a steel miracle, a desert highway stretching over 500 kilometers, cutting straight through this sea of death. The project cost the Xi Jinping government nearly $3 billion and required tens of thousands of workers to labor under 70 degrees Celsius heat and blinding dust storms, where even a small mistake could see the entire road swallowed by the dunes. How did Chinese engineers manage to tame one of the harshest landscapes on Earth to carve a highway through this golden hell? Let's uncover the secrets behind this incredible feat with Mandarin Tech. In the far west of China, between two towering mountain ranges, lies the vast Taklamakan Desert, an endless ocean of sand at the heart of Xinjiang. Before the highway existed, crossing this land meant walking for weeks, even months, through one of the harshest environments on Earth, where surface temperatures can soar above 70 degrees Celsius, and sandstorms can swallow entire convoys in just minutes. Yet beneath that sea of sand lies a hidden treasure, enormous reserves of oil, natural gas, coal, and rare earth minerals. Strategic resources that have helped China strengthen its global position. To extract, transport, and connect Xinjiang with the rest of the country, Beijing had to attempt the unthinkable: build a highway straight across the Taklamakan Desert, a place once deemed an impossible blind spot for engineering. The Luntai-Minfeng Expressway, stretching more than 522 kilometers, began construction in 2017 and was completed in 2021, becoming China's first and longest desert-crossing highway. And the construction of the highway started from scratch, in the middle of a sandy desert. How do you build a highway across a desert that never stops moving? They began with high-resolution satellite imagery, ground-penetrating radar, and thousands of wind measurements to map the shifting dunes and find pockets of stable ground. Survey teams lived deep in the Taklamakan for months, drilling hundreds of boreholes, some more than 30 meters deep, to study the layers hidden beneath the sand. Every route marker was staked by hand and logged with centimeter-level precision. The highway had to avoid the wind corridors, where sandstorms could bury an entire road overnight, yet stay close enough to reach the oil and gas fields spread across the Tarim Basin. It was the first step in turning what had long been a blank white void on China's map into a black ribbon of pavement cutting across the heart of the desert. Before any concrete was poured or asphalt rolled, the project began with an unexpectedly low-tech mission, anchoring the sand. Hundreds of local farmers from small oasis villages along the desert's edge were recruited, earning between $80 and $100 a month, a humble income, but one that kept their families afloat. Their job sounded simple, yet it would determine whether the entire highway could exist at all. Bundles of straw, twigs, and thin bamboo were tied into long sheaves and driven deep into the dunes, forming a vast checkerboard pattern. Each square measured 1 meter by 1 meter, laid diagonally at 45 degrees to deflect the wind and trap sand inside the grid. Under a sun that pushed the air above 60 degrees Celsius, hot enough to bend metal, teams of a dozen men and women planted grid after grid across the desert floor. They wrapped their faces in cloth, soaked their hats with water, and worked in silence against the relentless wind. Within months, the transformation was visible. More than 1,000 hectares of straw grids pinned the dunes in place. Wind velocity near the ground dropped by 40%. The sand began to crust and harden, and for the first time, heavy trucks could cross without sinking. The checkerboards didn't just stabilize the site, they created new zones of life, protecting nearby villages and giving native desert plants a foothold again. From this quiet, back-breaking labor rose the first layer of an engineering triumph. On that newly anchored sand, the construction of the Taklamakan Desert Highway could finally begin. After the sand surface had stabilized, the next challenge was to reshape the terrain. Hundreds of bulldozers were deployed to flatten the dunes, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems pushed the excess sand away from the work zone, while compactors gently pressed the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. After the surface had been compacted, workers began spreading a base layer of soil over the stabilized sand. Dump trucks poured out loads of reddish earth, which bulldozers then pushed and leveled across the area. This layer added weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Each section was evenly spread and compacted, forming a dense, stable base strong enough to support the first stages of construction in the desert. Beneath the desert highway, the foundation had to be rebuilt from the inside out. The Taklamakan sand was fine and dry, unable to bear the weight of even a single truck. Engineers drove sand compaction piles and mixed cement directly into the soil, creating dense vertical columns that acted like roots beneath the road. In looser areas, geogrid mats, strong synthetic nets, were laid down to spread the load evenly. Once reinforced, convoys of dump trucks arrived, pouring crushed stone and grated gravel across the route. Bulldozers spread the mix into layers 20 to 30 centimeters thick, followed by vibratory rollers pressing it into a solid platform. By the end of this stage, the pale gray subgrade stretched like a giant runway through the dunes, ready for its black asphalt skin. At the edge of the desert, portable asphalt plants roared to life, heating stone, sand, and polymer-modified bitumen to nearly 170 degrees Celsius. From these stations, insulated tankers delivered the hot mix non-stop to the paving machines waiting on site. Each paver spread the glowing asphalt in layers about 6 centimeters thick, while steel rollers followed close behind, compacting it before it could cool. This process was repeated in a tight choreography, paver, roller, finisher, moving forward like a synchronized machine. The first passes used heavy steel drums for compression. The final ones switched to rubber tire rollers, which kneaded the surface to seal tiny air gaps and create a smoother texture. Thermal sensors on each paver tracked the surface temperature in real time. If the asphalt dropped below 140 degrees Celsius, rolling stopped immediately. Otherwise, cracks could form once it cooled. Supervisors checked flatness with laser beams, allowing no more than 3 millimeters of deviation per meter. As the desert wind cooled the surface, the asphalt hardened into a flawless black sheet, tough enough to withstand temperature swings from minus 25 to plus 70 degrees Celsius. To finish, workers sprayed a protective seal coat, giving the surface its signature deep shine and locking out moisture. By dusk, the newly paved highway gleamed under the sinking sun, a dark, mirror-like ribbon stretching across the golden sea of sand. What had once been an empty wasteland now reflected the light of progress, born from heat, steel, and human endurance. So after 4 grueling years of construction, the 4-lane highway cutting across China's largest desert finally stood complete, a powerful testament to human determination and technological mastery in the heart of the Sea of Death. This project not only connected the far ends of Xinjiang, but also showcased an engineering achievement so remarkable that even American engineers couldn't help but be impressed. But the story didn't end there. What came next left even seasoned American engineers astonished. A project on an even grander scale. Stretching boldly across the same unforgiving sands of the Taklamakan, China began constructing an elevated railway, a steel ribbon suspended above the desert, defying heat, wind, and time itself. The Hotan-Rokyang Railway, stretching 825 kilometers, is part of the larger Taklamakan Desert Loop Railway, which spans more than 2,712 kilometers. Construction began along the southern rim of the Taklamakan Desert and was completed in June 2022, making it the longest desert crossing railway in the world. More than 65% of the line, over 500 kilometers, was built on elevated concrete viaducts supported by more than 11,000 pillars. This design allows desert winds to pass freely underneath, preventing sand from burying the tracks. The first steps to build a railway track are to fix the soil and sand foundation, which is exactly the same as building a highway, so I won't repeat it again. Once the ground base was fully stabilized, workers began erecting the bridge pillars. To build them, they had to drill through dozens of feet of loose sand until reaching the solid gravel or compact soil beneath. Reinforced concrete pile drivers operated day and night using steel casing pipes and bentonite slurry to keep the boreholes from collapsing. Concrete was poured from the bottom up through tremie pipes to prevent air pockets, while the steel cages were positioned with millimeter precision. Even the slightest misalignment could cause the pile to tilt or lose stability. Because daytime and nighttime temperatures differed by more than 130 degrees Fahrenheit, construction crews worked mostly at night when the wind was calm and the sandstorms eased. Thanks to these steel and concrete piles, the railway's foundation seemed to grow roots deep into the desert. On top of those foundations, 11,000 bridge piers began to rise, row after row, forming a vast concrete forest stretching across the desert. Each pier stood between 16 and 50 feet tall. The shafts were cast using slip-form molds, reinforced with galvanized steel and salt-resistant additives to withstand the desert's corrosive climate. The short, uniform spans between piers were designed to minimize the effects of wind and extreme temperature changes. As the sun set behind the Kunlun Mountains, the endless lines of pillars stretched toward the horizon, a skeleton of steel and concrete, unshaken by the desert winds. On top of those pier caps, thousands of pre-stressed concrete box girders were lifted into place using heavy crawler cranes or self-launching gantries. Each girder was over 100 feet long and weighed several hundred tons. They were transported on specialized flatbed rail cars and hoisted one by one onto the piers. Engineers then aligned the girders with laser precision, keeping tolerances within just a few millimeters. Once the spans were secured, crews poured the bridge deck slabs or installed precast concrete panels, forming a smooth surface for the tracks. Every span was spaced to allow wind to sweep freely beneath, carrying drifting sand away so it could never bury the line. More than 65% of the Hotan-Rokyang Railway, about 310 miles, runs on these elevated viaducts. From above, the railway appears like a silver ribbon cutting across an ocean of gold, a living monument to human ingenuity against one of Earth's harshest landscapes. Next, these concrete blocks being installed are called sleepers, or railroad ties. They're placed evenly along the track bed to hold the steel rails in position and distribute the weight of passing trains. Workers align each sleeper precisely, then use a lifting frame to lower the rails onto them. Once fixed and fastened, they keep the track straight and stable, preventing it from bending or shifting under heavy loads. A crucial step before the trains can safely run through the desert. After the sleepers were secured, crews began laying the steel rails on top. Each rail, stretching more than 260 feet long, was lifted into place by specialized cranes and carefully aligned along the center line. Workers adjusted every joint and gap to allow smooth expansion under heat, then tightened the fastening clips that locked the rails onto the concrete base. It took 11 months of continuous work to complete the hundreds of miles of track stretching across the desert. When the final bridge span was completed, the entire line entered the testing phase. Engineering trains ran up and down the route to measure settlement, vibration, rail temperature, and wind-induced sway. The bridges were load-tested with trains weighing thousands of tons. Results showed elevation deviations of only a few millimeters, even after hundreds of test runs. Thanks to the elevated design and natural airflow beneath the viaducts, no sand accumulated on the tracks. All operational data flowed to the control center through IoT sensors and solar-powered cameras that monitored every section in real time. After 6 months of rigorous testing, the Hotan-Rokiang Railway officially opened in June 2022, completing the 1,685-mile loop that circles the Taklamakan Desert. So you have learned the whole process of building a road through China's largest desert. If you are impressed, follow Mandarin Tech so you don't miss any interesting videos.